Okay, before we start the next example, let me talk briefly about these things that we call massless frictionless pulleys and massless ropes. Okay, um, so imagine this pulley. This pulley is frictionless, which means that the axle here is frictionless, and then the rope also goes over the pulley in a frictionless manner. Um, the rope is massless, the pulley is massless as well. Okay, so when all these assumptions are true, then the implication is that if you consider a single rope like so, the tension in that rope is a constant. In other words, the tension here is the same as the tension here, is the same as the tension here, and so on, wherever this rope goes. Similarly, if you have the same kind of pulley like so, the tension here is going to be the same as the tension here, and so on and so forth. Okay, if you have multiple pulleys, doesn't matter. As long as it's a single long rope, the tension remains constant. If you have a massless frictionless pulley and massless ropes, if any one of these assumptions are falsified, in other words, the pulley has mass, or there is friction somewhere, or the ropes have mass, then the tensions can be different. So where does this assumption or where does this claim come from? It actually comes from a topic that we have not officially covered so far, basically moment balance. You would have seen sort of a statics version of this, but this is the dynamics version. But basically, if you take moments about this point, then for the pulley to not accelerate arbitrarily fast, essentially the moment due to this tension and this tension need to cancel about this point, so the tensions should be equal. So that's basically the argument um, for this. Because the object doesn't have mass, it turns out that the total moment should be equal to zero. Okay. So again, like we said, we'll talk about this later on. But to actually do the problems right now, we will need to actually use this principle that the tension remains a constant. Okay. Later on in the course, we will actually have pulleys with masses. Okay, we'll have pulleys with masses and with friction potentially. And we can no longer assume that T is a constant. So imagine a pulley like this and a rope that goes like this. If the pulley has mass, then the tension on this side might be different from the tension on this side. So that's possible, but that's only when the pulleys have masses and or friction. If the pulleys have neither, then this is true. Okay, pulleys have neither, and then the ropes are massless, then the tensions remain the same. So this is what we will do for the first half of the course, and then in the second half of the course, we will talk about this. Okay, so first half of course. Later in the course. Okay. Okay, so having said that, let's actually do another pulley problem. So we have a pulley here, which is connected to a mass, and you're pulling on a rope like so. Okay. Actually, let me do this. Okay, so that it's actually downward. Okay. Okay, so we have a pulley like so, and someone is pulling the string on the pulley downwards. And the question is so of course pulley is massless and frictionless. ropes are massless and inextensible. I didn't quite mention this, but when we say massless and frictionless pulleys, we say this is sometimes called an ideal pulley. Okay, so that's what we mean. So this is called an ideal pulley. And this would be called an ideal rope. In other words, it satisfies a certain ideal. Okay, so those are the given things. Mass M equals, let's say, 10 kilograms. Let's say the force P is given to be 200 newtons. Determine acceleration of acceleration of mass M and of point A. Okay, so I guess those are the two questions. Okay, so let's look at the solution. What's the first step? The first step is always to draw the free body diagram. So the first free body diagram could be that for the mass M, and there's going to be tension pulling it upward. There's going to be mass mg pulling it downwards. That's the free body diagram for the mass. And then it's useful to draw the free body diagram for the pulley as well, potentially. So let me actually add another question here. A, B, determine force exerted by pulley on ceiling. Okay, so basically the force transmitted by this pulley on the ceiling. So I just added that question because I guess I want you to think about the free body diagram for the pulley. So this is the pulley itself. Okay, it's a pulley with the ropes attached to it, I suppose. So this side we have P, the force on the pulley, on the rope. That's basically going to be the tension, and it's going to be the force transmitted all the way here based on the principles that we just talked about. And then here, it's going to be something else, like T2 or something. Okay, this is a different rope. So the tension in this part of the rope is going to be different. So we can call this T2 or even T. So that's free body diagram number 2. This is for the pulley. Okay. This is basically what is being asked in part B of this question. For part A, basically this is equal to T, that's this thing, T equals P. Let's say the acceleration is defined as A, this is positive A, this is sign convention. Okay, this is positive A. So let's write sum of forces equals MA for this free body diagram for FBD1. We have mass times acceleration. This is the acceleration, and we are doing positive upwards. So equals, you can either say T or P, doesn't matter, they are equal. So P minus mg. And that's really the answer. A equals P minus mg divided by m. That's one answer. And then for this thing, well, we can write equations of motion for this pulley, right? So T2 minus 2P equals the mass of the pulley is 0 times the acceleration of pulley. So let me actually write, say, so A pulley upwards, right? So if you say A pulley is measured upwards, this is going to be an equation for the pulley, but because the mass of the pulley is basically 0, because this is 0, it's massless, we have T2 minus 2P equal to 0, or T2 equals 2P. Okay, and that's the answer, right? So this is basically 400 Newton. This is the answer for part B, and this is going to be answer for part A. Okay, so this is super important, this principle, where if you have a pulley where the tension in the rope is P and P going this way, you can basically do force balance to know that the tension on this side of the pulley is actually going to be 2P, because it needs to really balance these two forces. Okay, super important principle. So that's the end of that example.